right? So we were just telling you that the material that we have here has an endurance limit, so that question is done. But now it is a stress and number of cycles to failure. But if you have noticed, the brilliant thing is that here in this graph, a stress amplitude is directly given, a stress amplitude rather than the stress. So when I asked you that should we use the stress amplitude formula, because normally it is a stress, load upon area, but here it is load amplitude directly given. So when you calculate here, rather than you find the stress as load upon area, you find the stress amplitude directly as load amplitude upon the area, of course with the factor of safety. So this is it. Let us see, right? Of course, area is pi by 4 d square. They have written it like this, which is 2 square will be 4. And the stress, which is a stress amplitude here, is load upon area. So load upon pi by 4 d square. So this is the equation. This is the equation. And you can take the d on the other side and the stress amplitude and so on, you will see, right? You will see. So you get this equation. D naught is 4f upon. Now sigma upon n, this n here in this book is the factor of safety, because you don't take the stress amplitude, you take the factor of safety, right? So the load was given, remember, the load was given, yes or no? What was given? If you go back, right? Because one of these things is given in the problem, right? And the other you read from there, what at endurance limit, what is the stress amplitude. So you directly put in there and you get this answer, right? So again, you can leave the answer like this. This is technically correct, but not elegantly written, right? So you write 23.4 millimeter, 23.4 millimeter rather than 23.4 into 10 raised to minus 3 meter. Of course, remember, write everything in newtons and meters. Don't write in mega or kilo and so on. Write everything like this. Okay. So this is it. This was another example on fatigue. So we have done one example where we calculated the basic things, amplitude and stress range and so on. And here now, that if a material graph is given, Sn graph is given, or stress amplitude n graph is given for different materials. We did it for an endurance limit material where failure will not occur. Otherwise, on the same graph, we could say that this is the fatigue strength that we mean. We won't go beyond that. Or we need a fatigue life of say 1 million cycles. Then what should we do, right? So if there is endurance limit, then yes, below a certain load, it will continue to theoretically work with no fatigue failure. But if the curve is a continuously decreasing curve, then we can find that no, we want a design life of 1 million cycles or 500,000 cycles, and therefore what should we do? Okay. Now, structural changes in the fatigue process. You see, remember, we have talked about failure under impact loading. We have talked about failure under tensile loading when we keep on increasing the load and how does the crack propagate. Now there is fatigue loading. So what changes happen structurally inside the material, right? So crack initiation first occurs. Crack initiation first occurs. Now we have told you earlier that during primary manufacturing and during secondary manufacturing, some cracks or flaws are already generated, mostly in all of the normal materials. So this crack initiation is therefore already done. But if the material is in a very good condition and there are no major cracks, they are so small that we can neglect them, then this crack initiation is the first stage. So there will be fatigue loading and it will keep on happening until that happens. Then there is something called slip band crack growth. Slip band. Remember, right, from your material science, that materials have slip planes along which the material can deform more easily, right? So plastic deformation in one direction, and then the reverse direction causes surface ridges and grooves called slip band extrusion and slip band intrusion. So you see there is a slip band, load is going there, but then it hits a grain boundary, direction may change. So some ridges means the small flaws and so on. Surface irregularities and damage along persistent slip bands. Surface irregularities and damage. Cracks form and propagate into the material along planes of high shear. So this is based on your earlier material science, that there are slip bands which are from material science, and if we keep on applying fatigue load, some surface irregularities can be there, and then they will try to propagate. So this surface irregularity or a small crack will start to grow. Propagate means grow. So this is called a stage 1 of fatigue crack growth. A stage 1. It is slow in nature. It takes a long time. Right? Of course, this 10 raised to minus 10 meter is 10 nanometer, right? And so on and so forth. Or the other way around, 1 upon 10. Then there is a stage 2 crack growth on planes of high tensile strength. Crack growth changes direction to perpendicular to the maximum tensile stress condition in polycrystalline material. Remember when we were describing cup and cone fracture, then we told you that this is the crack surface, this 90-degree direction is there, but when you are going close to the end, then you take a 45-degree line. So that is there. Well-defined crack propagation at relatively rapid rate, at some microns per cycle. This was 0.1 micron, this is several microns per cycle. So this is a stage 2. And finally, there is ultimate ductile failure. The sample ruptures when the remaining cross-sectional area is too small to withstand the applied load. So crack initiation, slip band crack growth are almost together. This slip band crack growth is called stage 1, then stage 2, which is the more standard fatigue crack growth, and finally critical area, sudden failure. So here they are showing you, right, if you take the micrograph, right, microstructural picture, then you will see that there are hundreds and thousands maybe of these lines, right, here or here and so on, and these are called slip bands. So each one of them is like telling you one fatigue cycle, and once the slip bands are there, then crack starts to happen, and later on it will grow. We will come back to it again, don't worry, right? Here we have just introduced to you that either small flaws are already there because of primary or secondary manufacturing, or because of this persistent slip band growth. You are applying fatigue loads, and there are slip bands in the material, and there are directional changes. The material starts to deform along the slip band. When it hits a grain boundary, there can be reversal or changes of directions. Those create or initiate the crack. Once the cracks are there, then they will start to grow. That is a stage 2. Then they will start to grow. The slip band is very slow. It takes longer time to form the crack nucleation. And once crack is formed, then number 2, stage 2, it keeps on growing, but it is stable. Even though it is growing, there is still life. Once, we will see later on, once it reaches a critical value, then there will be sudden catastrophic failure after some time. So we have done some of this earlier. Remember, K1 is equal to sigma root pi A. So from K1 we go to K1C, where the sigma, the applied load, has to be more than a critical load, or the A becomes AC, the critical crack size, and so on. But this time it is for fatigue loading, right? Fatigue loading. Now, factors affecting fatigue load, factors affecting fatigue strength. A material has fatigue strength, it can resist fatigue. What are the factors? Stress concentration, of course, first of all. Fatigue strength is reduced by stress concentration. So notches, holes, keyways, sharp changes in cross section, if they are there in the material, then of course a stress concentration will be there, and that means the fatigue strength of the material will be lowered. Surface roughness, another factor. A smooth surface increases the fatigue strength. If the surface is smooth, material has high fatigue strength. But if the surface is rough, roughness means stress concentration. But this is a stress concentration only at the surface. So surface roughness will again reduce the fatigue strength of the material. Other surface condition. Most fatigue failures originate at the metal surface. Surface treatments like carburizing and nitriding, they can increase the surface hardness, so the fatigue life can be increased, right? So surface roughness, or the opposite of it called surface finish. If the surface finish is good, material has good fatigue strength. If there is surface roughness or surface finish is bad, then the fatigue strength reduces. To improve that, you can do surface treatment. You can introduce carbon gas or nitrogen gas. It is called carburizing and nitriding. It is done at a specific temperatures and so on for specific metals. And then there is a strong surface layer. So now surface cracks can't grow so easily. Therefore, surface conditioning is one factor. Environment. In what type of environment are they working? Is there a chemically reactive environment which might result in corrosion, right? So if there is water or water vapor or dampness around, if there is salt or something around, right, then fatigue life will be decreased because of corrosion, right? Under corrosion, if there is a combination of corrosion and fatigue, cyclic stress, then it is called corrosion fatigue, right? So this is a very special case because this happens a lot. So therefore, whenever there is a special case, then it means this happens more than the normal things. So cyclic stresses are there, but together with that, the environment is such that there can be corrosion. So now you have a corrosion fatigue case, right? So these are the factors that affect the fatigue strength. So if we want to improve the fatigue strength, or if we want to delay failure due to fatigue, then we work on these factors. Can we improve the stress concentration? Can we improve the surface roughness? Can we do surface conditioning? Can we change the environment, and so on? So here that is what we are saying, right? Improving fatigue life, improving fatigue life. Now, this we have not talked about. This we have not talked about. Let us see first. You see, when you were doing the fatigue test, when we are doing the, fracture toughness test, so you had a sample, compact sample with a V notch, and then we were applying the load, right? Applying the load. The load was in mode 1, right? Mode 1 is also called what? Opening mode. Opening mode. Why? Because the tensile load is at 90 degrees to the crack surface. So when you apply that tensile load, the crack keeps on opening and enlarging, and ultimately it starts to grow, and then there will be catastrophic failure. What if we apply compressive load? What will happen to we are applying in mode 1. Mode 1 means the load is at 90 degrees to the crack. But if we are applying compressive load, what happens? The crack starts to close rather than grow, right? So compressive load is good for fatigue. Compressive load is good for fatigue. So one technique of improving fatigue life is to apply compressive stress to suppress surface cracks from growing, right? So you take a hammer, you do, right, hammer the piece. Of course, don't hammer it so hard that it damages, but keep on hammering so that it is also called shot peening. There is a machine where there are small balls, and all those balls start hitting the surface. So a small compressive stress which is designed so that it is not too large to crack the material, but good enough to close the cracks. So the first technique is impose a compressive surface stress.